Hi, all. So we have another great session now. But we have with us Florian and Fabian, who are security consultants at SCHUTZWERG Germany, and they're working on embedded system security. And today they'll be talking about PROBoter, which automates PCB analysis. And helps comes up with some interesting analysis and which can help with with penetration testing of PCBs. So with that, I'll pass it over to Florian, who will continue with this talk.
Thank you a lot for your introduction. So let me just share my screen. So today I will be talking about the PROBoter, which is an automating PCB analysis tool, which we here at SCHUTZWERG developed to support us for penetration testing of embedded systems, since our main focus is on the security assessment and consultants for also automotive systems, and therefore we had the idea that this tool will be helping us. First of all, I would like to introduce with the motivation for the background for this whole development. So cars, as you're probably aware of, are quite complex systems, and there was quite an increase relevance for cybersecurity over the past few years, which also led to new regulations, like, for example, the ISO SAE 21434. In cars, there are quite a lot of attack vectors, and here we want to focus on physical attacks, and here again, especially on black box testing, meaning that there is hardly any information available in advance to attack such, at least starting with one component of the car. So just to give you an idea how such a attack analysis is to be performed, I would like to introduce the usual way, the common way to perform a manual analysis. Manual analysis usually consists of 4 steps. First of all, doing a visual analysis on the PCB to be under test. This is followed by a static analysis to check for the interconnections between the components on the PCB. Third step is a dynamic analysis where the PCB is investigated in a running state. And finally, there is expected to be the attack. When doing the visual analysis, the first step is the identification of all parts which might be relevant on the PCB, meaning the search for data sheets and getting information on the functionality, which components might be interesting and which might be less interesting. So this is quite time consuming to identify all those various components manually, and also to get on the search for each of the data sheets. As you can imagine, as you see here for this example PCB, which is not from the automotive field to protect international intellectual property, there are quite a lot of components to be identified and also to search for the data sheets. The next step is the static analysis, where you use a continuity tester to check for all those more interesting components to see how those components are connected to each other by which pins, and which communication pins are also led out to each other. So quite similar to the previous step, the amount of pins which are used for communication between the components is quite large. And using a continuity tester here, for example, when using this chip, you see that the pads are quite small. So just by slipping off with your probing tip happens quite easily. So this gives you false information. The third step is the dynamic analysis, where you supply the board with a voltage and check for voltage signals that are occurring on that board to find out whether those already identified pins, or even so far still unknown pins, have some interesting voltage signal applied. For example, here in the lower left, you see that there is a voltage signal of some data transmission occurring, and this is actually something you are looking for, since using such a data transmission is at least there is at least the possibility to get additional information, or even to be able to inject some additional data into the communication. Here we face the problems that if one tip is slipping off from this intended position, you can either, in the best case, only disposition the tip and therefore supply or measure the voltage at the wrong tip, or worst case is that by supplying this whole board with a voltage, you actually create a shortcut between two pins, and there is the risk that this can actually lead to a damage of this component. The fourth and last step is the attack, and with some luck, you find some debug interface on the PCB to have the possibility to get a shell. And here in this example, were even able to get a root shell on the system to execute from there additional attacks. As you've seen, this whole process is quite time consuming and also quite error prone, and therefore we decided to develop an additional tool which we want to help us. This tool has been developed as part of the SecForCARs project, and we defined 4 targets for that tool. First of all, we want this tool to be able to perform a component and pin detection. Second is to perform the electrical net probing automatically to check which connections are there on the PCB. The fourth step is to measure the voltages that are occurring in an active state and perform an evaluation of those voltages that are occurring on that PCB. And finally, we want this tool to be able to assist us in an attack. As you can imagine, there were several iterations for this PROBoter tool during the development until it reached its final state. So here you have an overview on this PROBoter. It mainly consists of aluminum profiles, for which we got inspired from flying probe testers. For moving the probes, we decided to use stepper motors, and all those parts which were not available from the rack, we designed and produced in the SCHUTZWERG office by using 3D printed parts. For the components, we do have 2 types of camera systems. One static camera system from the above, which is supposed to give us a big overview on the PCB under test, and additionally also a movable camera system, which is connected to the probe to be able to take pictures with a more detailed focus. In total, there are 4 electrical probing units, and for each of the probing units, those are able to have a precision accuracy of 0.1 millimeters. So for all those targets, I would like to give you a bit more focus on 2 of those tasks. First is the component and pin detection for which we use the camera systems, as well as the voltage record analysis, which we use for the evaluation of the voltage signals that are occurring on the PCB. For the visual analysis, we use neural networks, for which we used two new PCB image data sets. And here we have a detection rate of 87.4% mean average precision to identify the components on the PCB. The second one is that we use neural networks and computer vision pipeline to be able to identify pins for each of the components. And here we have a detection rate of 80.6% mean recall. Coming to the dynamic analysis. For the dynamic analysis, the PROBoter measures the voltage creates a voltage data set, and then it uses several methods to gain additional information to perform a characterization on the measured voltage. And here it uses a histogram produced from the voltage states that are occurring in that voltage data set. It also uses the durations that of each of the voltage states. Then it also uses a delta analysis, which we developed here to be able to identify breaks between the transmission of bytes. And finally, it also uses autocorrelation to be able to identify self-similarity of the signal, as for example, as it is quite common for the UART protocol. Then finally, it takes all those different characteristic signal properties. This finally leads to all those characteristic signal properties which the PROBoter harvests for further evaluation. So here you have the example histograms. For example, on the left histogram, you have a histogram for the durations of voltage states, and the more often a certain duration happens, the higher the peak, whereas on the x-axis, on the horizontal axis, you see the actual duration of each of the reoccurring states. On the right side, you have this delta analysis plot, which leads to a staircase function. And as you can see here, we use the clock signal of an SPI transmission, that you do have quite similar durations for each reoccurring similar durations, which are then interrupted by a longer duration. And actually, this longer duration can be used as identification characteristics, since here you do have a break of the transmission and use this as a characteristic for the identification. So to give you an overview on this dynamic analysis, first of all, the PROBoter gets the characteristics of the signal properties, identifies the functionality of that signal, which might be that this voltage data set is measured at a electrical ground or a electrical voltage supply, can be the clock signal of a synchronous data transmission or a data transmission. From this information, it attempts to identify the underlying protocol, as well as linking the synchronous the synchronous lines together, meaning that when you do have a synchronous transmission consisting of a clock signal and a data signal, to use characteristics of each of those signals and try to find those partners to get those together. And additionally, the PROBoter attempts to identify the parameters used for the transmission of the signal. This is especially interesting in case of a UART transmission, where you do have various parameters to be set in advance, and in case of a black box test, you do not have this information available to be able to decode those voltages into data again. So far, this PROBoter tool is able to identify the following protocols: I2C, SPI, one wire, and UART, which are quite common in the automotive field. And for our samples, which we used for the development process, we were able to have an detection accuracy of 98%. So for all the theory which I have given you so far, I would like to give you a short demo which shows you the working of this PROBoter. Here you can see that this PROBoter can be controlled using a web interface, for which here we set up a new project. And in the first step, we order the PROBoter to produce a new image for this project. So the first thing it does is that it scans this PCB. It makes a photograph of it, and then we can request the PROBoter to run this neural network identification, which I mentioned before, for which you can see here that the PROBoter runs this identification and is able to identify all those 8 components. But here, as you can see, it's especially also interesting to request the PROBoter to also perform an analysis here for those additional debug pads, which we just marked manually. And here we can run this identification for the interconnection between those pads. So when we hit the probe button, as you can see in the upper right, the probes actually start moving and start connecting all those pads and supply those pads with a voltage on one probe, and tries to detect whether there is the voltage also applied on the other pad, which produces the information which pads are connected to what. This takes a certain duration, and we see here in the next step that the probing is finished. And here we have the result of all those probings. Actually, we do know that here those 2 pads should be connected, but so far the connection does not work. We know that there is this error, and we also already have an idea how to solve this issue. That still needs to be implemented. So in the next step, we ordered the PROBoter to run a measurement of the voltages. Here we use a prepared voltage data set, and it correctly identifies that to that pad the generating voltages come from a UART protocol. So we can tell the PROBoter to connect to those selected pads with the selected order, and to be able to measure the voltages, convert those voltages into data. And as you can see, when we tell the PROBoter to reset the power, we actually get a debug shell on the PCB, which even allows us to insert an inject additional commands and request for information. So what are the next steps for the development for that PROBoter? The PROBoter development is still ongoing, and there is still a lot to further enhance the functionality of this PROBoter. We plan to publish the PROBoter as open source, and you can also find information on this PROBoter as well as the source code and the designs for production of the PROBoter on our GitHub page. You'll also find additional information on the SecForCARs homepage. You will find the PROBoter video on YouTube, as well as that we publish latest information on the PROBoter in our SCHUTZWERG blog. So to wrap it up at the end, I have introduced to you the PROBoter, which is a tool that automatically performs component and pin detection, is able to identify interconnections on PCBs, to check for connections of pads and pins. It is also able to evaluate the voltages that are generated on the PCB to identify the underlying functionality, as well as the protocol, and ideally also the protocol transmission parameters. And in the end, it is also able to support us for assisted attacks. Thank you a lot for your attention. I think we still have time for a few questions.
Thanks a lot, Florian. And that was a fascinating talk. Like PROBoter indeed is doing quite a bit behind the scenes, and tackling some of the hard problems. So I think we're almost coming up on time. So we have a question in the audience. So let me just put the question on stage. So what is the smallest physical distance between pins where PROBoter can reliably measure without short circuiting elements?
Fabian, would you like to take over that question, or should I?
I've just answered this question in the chat right
Okay.
now. I was typing as
Oh, okay, I see
Florian
that.
finished this.
I see the answer now. Okay, so I guess perhaps we can pack some more questions, like since you've already answered that. So basically, like you also mentioned neural networks for visualization. Like how often do you actually have to like retrain your models and update your models in this case?
We actually don't do retraining. We used our initial data set, which you also can find on our GitHub repository. And this model works quite good at the moment. So we didn't have the requirement to retrain. Yeah, can be done, but at the moment we're happy with the accuracy.
Sure, that makes sense. And then basically, like once PROBoter map like identifies like the various protocols on that circuit board, like is it also hooked into, let's say, like some sort of a penetration testing platform which can then automatically like perform the desired penetration tests, or is that more manual at this point in time?
And the identification of the underlying transmission protocol runs pretty much automatically, gives you the result which protocol has been identified, and from there you are free to continue whatever you like, whether you want to use your own probes to connect to the PCB and start to connect to the component.
That makes
I
sense.
think,
Yeah.
Abdul, you meant the data storage, the result storage and integration in other platforms? Well,
Yeah. I guess like I was wondering that like once you collect that data, like is it automatically hooked to, like, let's say, like in the back end, does it automatically hook to a penetration testing platform which can then, based on the data that you've gathered, like automatically perform some penetration tests and give out the results, right, without a human basically being in the loop at all?
yeah, we have a database in which we store all results. So regardless of which tasks we performed manually or automated. So the visual analysis results are stored and also the measurements. Currently, we use our own backend for this, but because the software is open source or will be released under open source license, yeah, I think it's easy to integrate or develop some kind of data integrator into other platforms as well.
And like we already on time, so I think we all almost like 1 minute over. So great talk, by the way, guys, and like really enjoyed it. And yeah, like thanks a lot for your time. And there's also a networking lounge in case you want to join and people have more questions and want to talk to you. But yeah, like great talk, and thanks to the audience as well for their time. With that, I'll end the session.
Thank you very much for having us.
My pleasure.